Okay, thank you. Good morning, everyone. I'm gonna talk about one interesting problem from computational biology, which is called DCJ medium problem. So the story starts from genome and evolution. So we know that usually genome contains several chromosomes, and each chromosome is a long sequence of base pairs of A, C, G, and T, and some genes may locate on the chromosomes. So during the time of evolution, some base pairs may change into other base pairs, and some may get deleted or inserted. So we call them a point mutation. In addition to that, genome also undergo large-scale evolutionary events, which can be divided into two categories. One is called gene content modifying events, like segmental duplication or large-scale insertion or deletion. The other is called rearrangements, like inversions, translocations, which will not change the content of the genome, but may change the order, direction, or position of the genes on the chromosomes. So we are interested in rearrangements, but before that, we first would like to give a mathematical model for genome. So very naturally, we model each genome as a set of chromosomes, and model each chromosome as a linear or circular list of genes. So each gene has a sign which specifies the direction of this gene on the chromosome. So here you can see one example with one linear chromosome and one circular chromosome. We have some terminology. We call the two ends of a gene as extremities. One is head and the other is tail. And two consecutive extremities form one adjacency. And we call the two ends of a linear chromosome as telomeres. So very clearly, for a linear chromosome with n genes, we totally have two n extremities. And those two n extremities form n-1 adjacencies and two telomeres. And for a circular chromosome with n genes, it also has two n extremities, which are grouped into n adjacencies. So we can use a capping method to remove the telomeres of the linear chromosome to transform them into circular chromosome. So in the following, we will assume that genome only contains circular chromosomes. This also simplifies the notations and the algorithms. Okay, we can use a graph to represent genomes. So like in this example with 6 genes in total, we can first list all the 12 extremities to the graph as vertices. And for each adjacency in the genome, we add one edge to the graph by connecting the corresponding two extremities. And you can see the 6 edges form a perfect matching of the graph. On the other hand, if we have a perfect matching, then we know all the adjacencies, and we can recover the genome accordingly. So there is a one-to-one corresponding between the perfect matching of the graph and all the different genomes on the same set of genes. Okay, you know what is genome and how to represent it. Now we introduce the rearrangement model. We use the double cut and join operation, or DCJ for short. So a DCJ operation just takes two adjacencies in the genome as input and output two new adjacencies by recombining the 4 involved extremities in one of the two cases. So let's say one example, a DCJ operation takes these two adjacencies as input, and one possibility is that the extremity of 4 head is combined with 7 head. And you can see the segment of 5, 6, and 7 is inverted. And the other possibility is that the 4 head is combined with 8 tail, which will produce 2 new circular chromosomes. And this path is also possible. So with this rearrangement model, a very basic and natural question is to ask, given 2 genomes, G1 and G2 on the same set of genes, what is the minimum number of DCJ operations needed to transform G1 into G2? So we call this problem as the DCJ distance problem. And very interestingly, this problem can be solved by a very simple linear time algorithm. So how? Remember the graph representation of the genome? So now we can draw the two matchings together on the same graph, like this. So very clear, in the graph, each vertex has exactly degree 2. So the graph consists of vertex disjoint cycles. And the DCJ distance denoted by d, g1, g2 is exactly equal to half the number of vertices in the graph minus the number of cycles. So we use the symbol say g1, g2 to denote the number of cycles in the graph formed by the two perfect matchings. So in this example, we have totally 12 vertices and 3 cycles. So the distance between g1 and g2 is 3. Okay, now we know how to compute the DCJ distance for 2 genomes. Okay, let's move forward. Given 3 genomes, g1, g2, g3, on the same set of genes, we would like to compute a 4th genome G, such that the sum of the pairwise distances between the 4th genome G and each of the given 3 genomes is minimized. Of course, an equivalent description of the problem is that given 3 perfect matchings, and we would like to compute the 4th perfect matching such that the sum of the number of cycles between the 4th perfect matching and each of the given perfect matching is maximized. So we call this problem as the DCJ median problem, and it has been widely studied and applied on phylogenetic construction and comparative genomics. So unfortunately, the DCJ median problem is NP hard, and several heuristics and exact algorithms have been proposed. So among these exact algorithms, one of the very promising work is done by Xu in 2008 and 2009. He deeply studied the structure of the problem and found an optimal substructure called adequate subgraph. And he also implemented a fast solver using adequate subgraph. So let's see what's the detail. Okay, that's the definition. So we say the we say 3 matchings is adequate if we can find a certificate matching G such that the sum of the number of cycles is no less than 3/4 times the number of vertices. So we use an example to explain this definition. So we want to verify that these 3 matchings is adequate. One matching is red, one is blue, one is green. Notice that some matchings is not perfect. For example, the blue matching here, because the leftmost and the rightmost vertices is not covered by blue edge. So to see that this 3 matchings is adequate, we need a certificate matching, like this black matching. And then we count the number of cycles. So between the black matching and the red matching, we have 2 cycles. Between the black and the blue one, we have only 1 cycle. The path is not counted. And for the black matching and the green matching, we have 3 cycles. So totally we have 6 cycles, which is no less than 3/4 times 12. So that means these 3 given matchings is adequate, and this black matching is a certificate. Okay, why do we need adequate subgraph? We have a very helpful decomposition theorem. So let x prime is a subgraph of x, and if x prime is adequate, then for any optimal solution of x prime denoted by g0 prime, we can find an optimal solution of x such that g0 prime is a subset of g0. g0 is one optimal solution of x. So again, we use an example to explain this. So this is x with 3 perfect matchings, g1, g2, g3. Suppose we find one subgraph of x prime, and x prime is adequate. Then we can take x prime out and solve x prime independently. Let g0 prime as the optimal solution of x prime. Then the above theorem guarantees that g0 prime is also part of the optimal solution of x. So we can use G prime, G0 prime to simplify X to get a reduced problem, for example, X bar. Then we can continue working on X bar. And the optimal solution of X bar plus the G0 prime is one optimal solution of X. So this decomposition theorem gives us a very efficient algorithm to solve the DCJ media problem. So we can first identify adequate subgraph in the whole graph, and then solve them independently, and then continue. So one key problem in this algorithm is how to find adequate subgraph in the whole graph. So to do this, Xu enumerated all the possible small adequate subgraphs and put them in the pool. So you can sum of them here. So each time he will compare the whole graph to each of the adequate subgraph and to see whether the adequate subgraph is a subgraph of the whole graph. But we know that subgraph isomorphism problem is NP complete. So this limits that we can only use very small adequate subgraph. On the other hand, we know that there are infinite many adequate subgraphs, but the pool can only contain limited many. So it is possible that the whole graph contains some adequate subgraph, but it is not in the pool. So it seems that this is not a perfect solution. So we propose a new algorithm to find adequate subgraph in the whole graph. So recall that to verify 3 matching is adequate, we need a certificate. Now we assume that a certificate perfect matching is given, denoted by G. So we ask the following question. Is there any, we ask the following problem. Is there any adequate subgraph that uses subsets of G as a certificate? So like in this example, we have one adequate subgraph, and it uses the given 2 black edges as a certificate. And we found that this problem can be formulated can be solved by a network flow formulation. Okay, let's see how it works. So we have 3 perfect matchings, and we also assume that a fourth certificate matching is given, like the black one here. So to build the network, we first list all the extremities to the network, and the second step is to add 1 vertex for each cycle. So you can say between the black matching and the red matching, we have 2 cycles. So we add 2 vertices to the network. And we connect the corresponding extremities to the cycle. And between the black and the blue, we have 3 cycles. So add 3 more vertices and link the edges to the corresponding extremities. And we do the same thing for the green one. So the third, we add 1 source vertex. We add 1 source vertex and connect it to each of the extremities. And finally, we add a sink vertex T and connect to each cycle to T with capacity of 1. Oh, sorry, I forgot to say the capacity assignment. So between the extremities and cycles, we have capacity of infinity. And between the source and each of the extremities, we have capacity of 3/4. Okay. So with this network, we now compute the maximum ST flow and also compute the residual graph with respect to this maximum flow. And in the residual graph, we compute the set of vertices that can reach T. And we call this set as capital T. And this is our main theorem. We proved that there exists adequate subgraph uses the subset of G as a certificate if and only if the capital T contains more vertices than sink T. And if such adequate subgraph exists, we can always find one out from the residual graph. Okay, this is our algorithm to find equity subgraph. So now let's move forward to another aspect of the DCJ media problem. It's bounds. So we have three notations. First, we call the optimal solution of the DCJ media problem as the median. So denoted by J0 as we used before. So we call the optimum value as the median distance. And we call the sum of the three pairwise distances between the three given genomes as a triangle distance. Notice that the triangle distance can be computed very easily. So we want to build the connection between the triangle distance and the median distance. So due to the triangle inequality, we have a lower bound of the median distance, which is half of the triangle distance. And each genome also give an upper bound of the median distance. So we have an upper bound of the median distance, which is 2/3 of the triangle distance. So I have two simple bounds. So one question is to ask, is these two bounds tied? So we have already know that the lower bound is tied. And an example can be constructed very easily. And now we prove that the upper bound is also tied by providing such a tight example. And actually, this component is adequate. So we can build a general graph by adding an arbitrary number of such component. Okay, these two bounds are tied. So another natural question is to ask, given an instance, is the lower bound or upper bound can be reached? So we found that the equalness to the bounds is closely related to the substructure, we call it strong pair. So we can define the strong pair as two vertices, and it can increase the number of cycles by 2. Okay, we use an example to explain this. We focus on the pair of UV, and we can replace the two edges in G1 by two new edges like this, and we can replace the two edges in G2 by two new edges like this. If these two operations can increase the number of cycles by 2, like it did in this case, we call the UV is strong with respect to G1 and G2. And we see UV is strong with respect to G1, G2, G3 if it is strong with respect to G1 and G2, G1 and G3, and G2 and G3. And we have the following two results. First, the median distance can reach its lower bound if there are V/2 number of independent strong edges. And the median distance can reach its lower bound only if there's no such strong pair. Okay, but the second result is not sufficient, and this can be showed by this example. In this example, it has no strong pair, but the upper bound is also reached. Okay, now comes to the conclusion. We contribute to the DCJ media problem in 3 aspects. First, we propose a new algorithm to find the adequate subgraphs using a network flow formulation. And we also prove that the upper bound for the median distance is tight. And we also study the conditions to decide whether the equalness can be reached. Okay, thank you very much for your attention.